Okay, good afternoon. Welcome to the first day of this Cadence tutorial. Uh, I am Miraj Ahmed from the research scholar from the Department of Electrical Engineering. I will talk on first on why do we first of all why do we need a simulator at first place? Can we do all those things manually using on pen or paper, or what is the difficulty? Why we are using Cadence? We will build up the motivation for using it. So if you see this, it is a simple non-linear circuit, very simple non-linear circuit. We have a resistor connected in series with the diode, and it is excited by a voltage source. Now, if in place of this diode, if we had a resistor of same value of R, the solution to solve this is pretty simple. You can easily apply KVL, KCL, and if even it is a complex of linear circuit, you can uh, easily solve using determinant matrices, Kramer rules. So these are things which we studied in network theory. But what is the problem with non-linear circuit analysis, why this simulator will help us to do many of this analysis? So if you see here, we have a non-linear element, this diode. The current is a function, exponential function of the potential difference across it. So now to solve this type of, and the other equation we have is the ID is equal to Vs minus Vd by R. So now to solve these two equations, we cannot use those linear equation techniques which we have learned earlier. So in engineering mathematics, we study some more techniques which we call as Newton-Raphson method. So these methods are being used by a simulator. We can do it manually, but it's very cumbersome and time taking. As you can see now, the above two equation, if you want to eliminate ID, we have this term. On the left, we have VD, on the right, we have exponential of VD. So it is not possible to just simply get the solution of VD directly. We need to iterate. If you can brush up that how Newton-Raphson work, if we iteratively find this VD, and we need to there is no fixed number of steps required to get the value. We need to have an initial guess, and based on that we will just estimate and come near to the solution. So this approach, this is what simulator does actually. Whenever you have nonlinear element, it tries to find the solution and gives you the value. So it saves your time in those very cumbersome analysis. Just for completeness, this is one approach. There is also one approach which we call graphical methods. If we know the characteristic of this diode, and if we know, if we plot the other equation, we can come up to a solution very easily. This approach will help later when you design a circuit. There are methods like GM by ID technique, ID by W. So people have evolved, and they can even in design it pretty helps. So this is not in the scope of this workshop, but just for completeness I have said. Now we will see some simulation in Cadence. So first of all, uh, what are the basic analysis we would like to do, especially with a non-linear elements? So I hope you are familiar with small signal diode analysis. If not, there is a very good video lectures from Professor Shanti Pawan from IT Madras. You can go through and through this video lectures, EC 2010 analog circuit. You can just go through at least 4 or 5 lectures from the beginning. So it covers in detail all what I'm talking right now. So now what happens if in place of a DC source, you have some AC signal? So how this circuit will react? What will be the output across the diode? So for DC, it is similar what we have seen in our previous slide. Using Newton reference, our simulator will just pop up these values. And for AC, what it does, in AC, it linearizes the circuit. So uh, I will tell it again that it's better you go through these lectures, like how to linearize a circuit, like how to linearize an element like diode, resistors, transistors. So if we linearize a diode, we'll get an equivalent resistor of eta Vt by Id. So, so for our interest, like if we see our audio amplifiers, we have our voice tone, it is an AC signal. So how our voice will process, how it will be conditioning using the circuits, we'll see. So we need these two types of analysis. One DC, it helps to establish the operating point, and it helps like how the AC signal will react to it. So based on these two, uh, we come to know that we need to have two analysis, at least AC and DC. And there is one also transient analysis, how with respect to time a signal is changing. So we will see these three analysis, and we'll say like how to simulate, how how we'll simulate this AC analysis and DC analysis. What are the parameters? If you can see that uh, the AC, this RD depends on ID. So just by changing the operating point, our AC behavior will change. So we'll do it in simulation and see. So now we'll go to, this is a brief regarding what analysis we'll do. We'll go to uh, Cadence. I will share my screen. So regarding the setup, I think it's pretty straightforward, which the steps can be given. So I will directly start with invoking our cadence. Virtuoso is a, you need to invoke. So So the first thing is we need to make a schematic. But as we saw here, in we will try to make this schematic in Cadence. So when we open Virtuoso, we need to open a schematic page. So we'll go to Tools, Library Manager. Here we have these three cells like library and cell. So you can think library as your notebook, and your every page is analogous to your cell. So if you want to make a schematic, so we need, first we need a if you want to make a schematic on your notebook, so you need a notebook, and on that you will draw. So first we will make a notebook where our all schematic will be saved. So CAD tutorials. Now uh, now if you see like this diode. So if you buy a diode from different vendors, the models will be different. The VT, the saturation, reverse saturation current, the eta value. So we need, so we know that we were designing circuit for a particular foundry. So based on that, we need to select some models which are given by the foundries. So in our case, which for our tutorial, we will use, we are attaching to a technology library, which is UMC 18, 180 nanometer. So this is needed so that whenever we use diodes, so all those parameters are taken from that model file. So CAD tutorials. Now, now in our notebook, we need a page on which we will draw the schematic. This is called our cell view. We can type any name, diode. So now we got a schematic. Now we can draw all our schematic here. So the first thing, uh, what is needed? Let's see. We need a resistor, we need a diode, we need a DC source. So to there is a shortcut. By pressing I, you can add any instance. So the library in which you will get all these terms, resistors, ground terminals, and our voltage source is in analog lib. In this, first we will, there are a lot of components. We are interested in our DC source. Now we can apply, suppose, 1 volt. One more thing, we are not supposed to give the units. It takes automatically, but we can give like, uh, if you want 1 milli, you can add 1 milli like this, but there is no need to give voltage. So now we have this voltage source. Now we need a resistor. RES is a transform 1 kilo ohm. If you press R, you can rotate any component. For wiring, you need to press W just by left clicking. And now we need a ground, GND. And now we need a diode. For diode, we will use the Foundry model files, so that we, so there are very variants. We will, for now, we will take any one. So this is done. Now the first thing you need to do is you need to save, and check and save is important because it creates the netlist. Now we need to run, and we need to find the DC node potential, like across this resistor, across this diode. We will try. So the simulator will do all this calculation and it will give ID and VD. So for that, we go to launch and click on ADE. So this ADE helps us in doing all those analysis and printing results. So there are various ways to go to analysis. First is this, choose analyze, or directly we can go from here and choose. So we are interested now in doing DC. We will save the operating point, and since it is enabled, it will appear in the analysis. Now this is the green button is used for running. So this has successfully you can see here. Now to see the node voltages. So there are various ways in which we can see the node voltages. So we can directly annotate on the schematic also. There is one annotate and DC potential. As you can see that across this voltage source we have 0 and 1 volt, here 1 and 7, 3.9 millivolt. So the simulator did it pretty fast. So if you have a very complex circuit, it's really very difficult to do manually. So for quick analysis, this tools really helps. Even ngSpice does the same thing. So now we are done with DC analysis. We got this VD. So what about now? What if we have some AC signal? We are coming here. If we have some AC signal here, how what will be the how it will behave? So we will add a AC source. Again, we'll press I, go to analog lib, and select V sign. So here, what we will do, there is one amplitude. We'll give 1 milli, and let's give a frequency of 1 kilohertz, and we will add in series. Again, we will check and save. So we have this AC current source. So if we want to see the transient behavior, how we time the output at this diode. So we'll also label the name of this net. Let's label it VD. We'll click on this. Our shortcut is L by pressing button L. So now this net will has been named as VD. So we'll do transient. Since our input frequency is 1 kilohertz, so that means the one period is 1 millisecond. So we'll run it for, let's assume, 5 milliseconds. This conservative and enabled, since we are using now we are now we are trying to view the time domain information of the circuit. So there are many differential equations that the simulator solves. So conservative is related to the accuracy, which I will talk in the end. So for now, we'll run it. So what it does, it just applies a real sinusoidal signal and it solves. And now we'll view the results. Go to result, direct plot, and transient signal. If we select and now click on the net, as you can see that around 703 was the DC value which we got from DC analysis. Over that, this is the AC signal. So we applied an amplitude of 1 millivolt, and now what amplitude we are getting is 700 millivolt. Peak to peak is around 350 millivolts. So why we are getting 350 millivolts here? This is 1K, and if you are getting less, it means that RD value is less than 1K, so that we are seeing attenuation here. So right. So now what we will do is, next thing, every time you would see, like whenever we simulate, we need to go to results. We go to results and use direct plot. We have a good option is we can add the plots directly here, so that whenever you run it, automatically plot it. So there are various ways. We can go to results, direct plot, main form. In that transient, we need a voltage, we want a net, and there is one option of add to output. If we click on this, and we need to select which node we want to save. So you can see add to output. Okay, then we need to click on the VD node, the color change, and it will appear in our ADE. So now whenever we will run this, so it will plot. Fine. One thing you might be thinking, like it's not a pure sine wave. So it's not because of the diode. It's because like since if you might have you may recall, like even Newton-Raphson, you need to iteratively arrive to a solution, but you will not be exactly to the solution. It's like how much accurately you are near. In some textbook problem, they will say you need to be 3 decimal places near to the solution. So there you stop your iteration. Similarly, in this calculating the transient, we have those differential equation, and how much accurately we want, we need to set it. So these options are there. In if you go in transient, option is there, maximum step size. I can give 1 micro, and you can see now this graph will be pretty smooth compared to, yes. So using a simulator is good, but you should know how the things are working, what are the parameters you need to set. Otherwise, you may be getting some wrong results just because your settings are not correct. If the previous sine wave, if you see, there are a lot of harmonics because it was not a pure sine wave. And if you see this yellow color uh, sinusoidal signal is much purer than the others. So your circuit might not be a non-linear circuit, but based on your accuracy setting, it will show that your circuit is non-linear. So we need to take care all these small things. I will also share some of the references where you can study about accuracy settings. Now we are done with transient. So this was one approach. There is also one way to add these type of outputs is using the calculator. This is very handy. It helps a lot in lot of our quick analysis. If we go in tool calculator, there are various options here on the top. Like if you hover or VT, what it's saying, it gives the expression of transient voltage. This is for if you want some AC voltage. Here this is for DC. So I will add all this. Suppose if I want any DC, I will select on this. Then I need to select on my schematic VD. So in the calculator, you got this VDC slash VD. Now I want to send this here in this ADE. There is this button. Whatever expression is there, it will just send to the ADE output. Fine. Now again, if I want to plot transient, I'll click on the transient. Then I will go on the schematic and select, and this is VT. Then I will send. Even for AC, even now we have not seen it. We can add AC also. So these parameters are added from the calculator. The good thing about the calculator is you can add some equation, you can, whatever signals you have, whether it is transient DC value, you can play with some mathematics, add some, uh, these are special functions. There is one all, there are a lot of functions available. You can manipulate the value as per your requirement. Now if I run, since I don't have VF, I will not plot. So here it gives the same output, and DC value is not plotted because it's a single value. So you will find that single value at this place only where we have in our AD output. The waveforms are plotted only if I have multiple values. So this is one thing. Now, like if you see like how this VDC, VT, VF, they read the values from this net VD. So if you see that whatever analysis we do, there is one place you will get all this information where it is called tools and result browser. If you can see in the left, we have all those DC information of all the elements. We have transient information. Now if we want to do AC analysis, we can add a term like AC. AC means you need, it will be, the x-axis will be in term of frequency. So for that we need to give some value. So generally how to set these values, it's pretty simple. Like if you know that your circuit is operating, your desired range of frequency or bandwidth of your circuit is, let's assume 1 kilohertz or 2 kilohertz, you can keep 10 times more to have a better view of what is happening. Now the moment I run this, this place you will get some AC. Yeah. So all these analysis are stored here. You can explore whenever you get access to Cadence. You can explore all these parameters. It's pretty handy if you have some big simulations. And so now as we have added the AC analysis, so what we want to view from it in this, in whenever we do AC analysis, whatever AC signal is there, we will get the equivalent potential here, AC voltage, whatever is there. So how we will check? Let's see. So when again we have many options. If I go to direct plot, this AC magnitude is also there. Either from main form also we can plot. So when we click, you can see the magnitude is 0. So why? So what we have done, we are trying to replicate this part. So we are getting 0 here. Why it is so? So in Cadence, you need to, as you have specified Vs, there is one separate location we need to specify the amplitude of this Vs. It doesn't take, so here we have applied a sinusoidal signal of 1 millivolt and 1K. So after linearization, whenever we do AC analysis, it ignores all these parameters. It ignores all this. So how the AC magnitude we can set, this AC magnitude is this AC magnitude. It is not even related to this amplitude what we are applying. So what it means is, if we see here, even if you apply 1,000 volt here, you will get a correct corresponding output. Why? Because while doing AC analysis, the diode is linearized and it is now a resistor of this value. So whatever you give, you will get. But if it is a transistor or a diode in DC, you cannot apply a huge potential. So it's not a realistic what do you call simulation in which you are applying that. So any value is fine. So generally we give 1 volt because if you see the transfer function output by input, if your input is 1 volt, your transfer function is your output. So it helps in many ways in analyzing the transfer function. So what we need to do is, okay, so we need to, okay, editing any instances by pressing Q. Okay, we have given 1 volt. Now we will check and save, and now we will run it. So now you can see that it's around 109. So you can back calculate if this is 109 millivolt. What does that mean? Is if you apply 1 volt here, you are getting 109 millivolt at VD. And you know that this is 1K, you can back calculate and find this RD. So this is the advantage of AC analysis. So it will help us when we'll see tomorrow, when we will make an common source amplifiers, like how AC signal varies and how we can control the gain of that is gain of that AC signals. We'll see that tomorrow. So now we are done with these. Now there are few very handy uh, options which really helps us in the easy working with cadences. Now suppose I want to change my operating point. Like we have seen, like if we change, if ID changes, the RD will change, and we will have the AC signal response will change. So how to change the operating point ID? There are various ways. We can play with R, we can play with VS. So what we'll do, we will change by playing this VS, changing VS. So now we need to go here and just we will apply some 2 volts, and whatever this green button is you are seeing in AD is also comes here. We can run from either of the two. So when you get access, you can explore all these buttons. So you can see like now it is 32 millivolts. Earlier it was 109. Why we have seen a change here? Because our ID changed, because we have increased the VS. Our ID increased, so this RD reduced. So effectively, it's a resistor divider. So we'll have a lower potential at this output. So now every time if I need to change and see that if I change VS, what happens? So every time I need to go and edit the schematic. So there is one way to set the variables. We can give any name like VS, and you can see that VDC is equal to VS, and go to your ADE variables, copy from cell view. Now you can directly put your variables here. Now if you run, it is for 1 millivolt, sorry, for 1 volt VS. Again it's 109. And every time you are seeing that whenever we run the simulation, the previous graphs gets erased. So there is an option like append mode is there. So what now, whenever we simulate, it will just overwrite. Now if we use 2 volts, so you can see this in the same plot. So these two are, all these are sine waves with different DCs, and these are our frequency response. So this variables helps a lot in many of our analysis, like how system will behave with different conditions. So now, since we have done with the variables, so there is one. So if I want to simulate iteratively, or I have simulated for 1 volt, simulated for 2 volt, can I do it automatically, that it can run for multiple times and by the changing the value? So there is one parametric analysis in tools where you need to select the variables what you need to sweep. So I have VS, I will sweep from, let's assume, 1 volt to 2 volts, and step will be linear of 0.1. So now if I run it, so there are 10 simulation, it will perform 10 simulation with different one with 1 volt, 1.1, 1.2. So what we are doing here is we are changing the operating condition, and in one plot you will be able to see all of them. Okay. So you can see this was a previous one. Let me delete. Just you can click and press delete. So the parametric analysis, what you are seeing here is these are the sine waves on the DC. The DC value is the operating condition is changing, and this is the frequency AC response. So in one place you were able to we were able to do and see the trends. Now we'll see like how we can use calculator and analyze these type of graphs for our ease. So you can see these all are sine waves and the amplitude is changing based on the operating condition. We change the operating condition, this RD changes, so the amplitude of sine wave will change. So can we do something like get a plot of amplitude of sine wave? So here, if you want to do this, the calculator function helps in this case. So what we will do, we will for every graph we'll calculate the peak to peak values and display. So for that, what we need is at first place, we need to go to the calculator. So this is one of the approach. Then we are interested in getting peak to peak. One option is take the transient of this node. VT. Now we are interested in peak to peak. So if you select all in function and just you find there is one peak to peak option. So it did peak to peak. Then you can send back to the ADE. So now you have this peak to peak. So for 2 volts, if you simply run it, you will get exactly what will be the peak to peak. It is 64.27 micro. Now if we again run the parametric analysis. So this, so using the calculator, you can analyze your circuits and get a more feeling of how things are just by how what are the things which are dependent on what parameters. So using parametric calculators, variables, it can use. So these are the things which are somewhat available in ngSpice, but not all, and in graphical way, which we get in here. So if we see here, you can see the peak to peak value on this node. So this yellow, how the peak to peak value is changing with the changing in operating condition, and it should fall because ID is there in the denominator. So effectively, um, so very in very just few clicks, you were able to see the trends, like how some parameter varies. So this, since it was a very small circuit with just 3 components, but if you have a larger circuits, so these options playing with calculators really helps a lot. Now some more things what we can do here is, yeah, we'll come to that. So solving this means we need to iteratively move on, and we'll stop based on our accuracy, like how much close this VD in the left and VD in the right is. Similarly, if the simulator also does the same thing, when we run DC, it does all this simulation and it has default accuracy settings, like what is the difference in the current, it can where it will stop the iteration and give the results. So if you go in simulation, option and analog, so these 3 important parameters are there: IF-stall, VF-stall and rel-tall. So these will be very helpful, like when you are working on very low current circuit design, in that your if you are not setting your accuracy properly, your results will not be correct. So that we need to be sure, like we should be very I think it's very important to know that what IF stall, VF stall, rel stall value we need to play. So I will share one document which talks about these numbers. So default value is good if you are in working in some millivolts. But if you are doing simulation in picovolts, so you cannot use this type of accuracy setting. You will definitely get some wrong results because this way the tools work. So it's good, like we should know a bit of how tool is also working. Now, what else? Some handy things are also there, like whatever settings we have done here in this AD, we have some option of like we can save this state and go to Selvo and give a name. I will just give a name like DC, AC, and trans. So where so where we can, as you can see, we made this CAD tutorial library, and this was our cell, and this is the schematic. Whenever next time you want to open, you can see in the bottom, this is a schematic we have made, and this is our saved state. So whenever next time you open, you can directly go to session and load. So it will load directly from the state where you are. You need not every time set your accuracy settings, set the input and output. So that's it. Okay, for understanding this, we took two sources, VS and this small AC and DC. Actually, if you see that, we don't need this bottom source, because this V sign have all DC voltage also. So it will add a DC, it will add some AC component, and this AC magnitude is completely different. It is only used in AC, and there this DC and this amplitudes are ignored. So we can put here VS and just eliminate. So we started only just for brief understanding. Now we can ignore it. And where is the parametric? So you will run, it will give equivalent results. You can see this 1.1 was there, 1.3. So these are calculated and these values are displayed. It is exactly equal. You can see that this was the previous one and this is the next one. It is overlapped. I would recommend like you go through this video lectures from IT Madras. So there they talk a lot about introduction to nonlinear network elements, incremental nonlinear networks. So this will really help you if you go deep dive. So tomorrow we'll start MOSFETs. So we cannot spend time on like how it is modeled. So if you see that the equivalent, this AC resistance is derived from Taylor series. So all these are covered in that lecture. So I think starting with simulation parallelly, you should go through all these lectures. You will find at IIT Madras video lectures, and this by Professor Shanti Pawan in this analog circuit will be pretty helpful. So this is that's it for today's tutorial. Tomorrow we'll see about common source amplifier, similar AC, DC, and transient analysis. And we'll do one more PVT analysis, process where voltage and temperature variation analysis. Okay, thank you.